All right. Case number 1. Case number 2. All right.
That one goes straight up the next piece. Thank you.
All right. If this is a meter stick, okay, and you've got the mass of the object, its center of mass is right here, and it's got its weight acting through its center of mass, or center of gravity, you'll hear that as well, and you push upward with a force equal to its weight, okay, will it be in equilibrium? Yeah, it will be. It certainly will be in equilibrium. Okay, now, what about this one?
No, it just falls.
It spins.
It falls, yeah, it spins around until it gets...
But, the sum of the forces in the y direction equals 0 here.
But they're not evenly distributed.
So its y acceleration is 0. The sum of the forces in the y direction here add up to 0. So its acceleration in the y direction must be 0. Right? Wait a minute, have I done something wrong?
Well, it's not at the center of gravity.
There?
It's not as
He's got the right idea.
Have I made 2 correct statements?
Yes. Not necessarily. Depends. On some of the forces of what? Yes. What?
In the y direction.
Of what?
No.
Of the forces acting on the meter stick.
On the what meter stick?
Okay, this is obviously a correct statement, right? This is a correct statement as well.
Yes.
No.
Yes.
They aren't being applied to the same point.
But that's not what this question, that's not what this,
Get out.
okay, that's a really good point. However,
Aggie's on it.
when we do this F equals ma in the y direction, how many forces in the y direction do we have? 2. I've got a force up minus an mg down equals ma in the y direction. These two are equal and opposite, so that's 0. And that is a true statement. However, this is messing with your sense of reality, right? Because we know that if gravity is pulling down this way and you push up this way with a force equal to that force, that it's not going to be the same as this one, right?
Because they're not at the same.
Because they're not at the same point. Okay, now, really important. Okay? Now, both of these statements are correct. What's disturbing you is that you know that this situation are not the same. But as far as F equals ma is concerned, they're identical. All right? Okay, so we need to come up with some new physics to describe the difference between these two situations. All right? Because they're not the same. However, in these two statements both say that the acceleration of the object must be 0. Now, we've talked about this briefly already, but when we talk about all the physics that we were learning this year, all the kinematics, all the F equals ma, all the energy, all the momentum, we're all talking about translational motion. Who do you need to talk to? You got it? We're always talking about translational motion. So remember when we talked about kinematics and you take an object and you throw it through the air? Okay, what's the only point on the object that we're really saying goes through a parabola?
Center of mass.
Center of mass, or the center of gravity, right? So when we're talking kinematics, F equals ma, energy and momentum, we're only talking about the motion of the center of mass. That's it. Just that point. All right? So we're only talking about the motion of the center of mass. We're only talking about the acceleration of the center of mass. We're only talking about what's going on with the center of mass here and here. When we're talking translational stuff. So look, the center of mass right here, will it accelerate? No. Okay, right here. Will the center of mass of the object here accelerate?
Yes.
No, it won't.
Not tangentially.
What's going to happen is the thing is going to rotate, right?
Change in
If
direction.
there is something to continue holding it on.
At this instant, right here, its center of mass will not accelerate.
Is it rotating about its center of mass, or is it rotating about something else?
It's rotating about the center of mass.
Okay, then yes, it will stay the same.
Yes. What's going to happen is you're going to, I can't do it on here because as soon as I let go of it, it's going to change, right? Because I can't keep that force in the same direction. But what's going to happen is if I push up here, it's going to rotate about the center of mass. That center of mass will stay put as I push this up. So what's happening is this part of the object will fall this way. This part of the object will push up, and the center of mass will stay put, at least for a little bit, as I push up on that spot. If I can let go, does that make sense? So if I can let go, push both at the same time. You see how it stays put? Now I can't stay put forever because it's going to eventually fall because I can't keep pushing it in that same direction, right? Does that make sense? All right. So the center of mass is still going to have a zero acceleration. Okay? Just like here, at least for this instant. But it is going to rotate, right? So we have to start a new type of physics to help us with this rotation stuff. Now, two things. When we're talking about rotational motion in Physics B, we're only talking about the very beginnings of it, okay? Not any of the hard stuff, okay? And we're only really going to talk about how you cause something to rotate, and then what happens when things are in static equilibrium. We're not going to really do any rotational dynamics, because that requires a little bit more math than we're prepared to do just yet, okay? So, in order to discover or to talk about how things rotate, we need to come up with a new term, a new idea, and that new idea is called torque. Okay? By the way, I wanted you to notice, I just erased it, but before, where the forces were located on the object didn't make any difference at all. So if I put mg here, or if I put mg over here, I put a force up here, and I put a force up over here, it wouldn't matter for translational motion. Remember how when we talked about free body diagrams that we're only talking about the center mass of the object, so whatever the object is, we just assumed it to be this point, right? That's it. So it didn't matter. For the first time, the shape of the object matters. Okay? It's going to make a big difference. So it's very important that when we draw our free body diagrams in this section, that we have the forces attached exactly where they're located and pointing in the right direction. Because if you don't, then you're going to be in serious, serious trouble. So we're going to start talking about a new concept called torque. Okay? All right, so you got a wrench. All right, so tell me, if you were to use this wrench, how do you use a wrench?
Like this.
Like these. Very nice. Thanks, Marcos.
Yep.
Okay, where do you apply the force?
Further and as far along as you can.
Okay, if you grab the wrench here,
That ain't gonna help.
not as good as if you grab the wrench here, right?
Exactly.
Okay, so first things first. in order to produce a lot of torque to cause something to rotate, because torque causes things to rotate, okay? In fact, there's our basic definition. Torque is a force that can cause rotation. Now, can cause rotation. It might not cause rotation, but it can cause rotation. All right? So, first of all, we've just learned that it's related to the radius, where you grab the wrench relative to the rotation point, right? Here's our rotation point right there. So you would grab the wrench out here. Okay, and then what would you do? Which way do you push or pull?
Depending on where you're.
Like this, right?
Yep.
Yes.
It
Exactly.
just falls off. Obviously, it would just come off the.
That just does nothing, right? So what do? You push this way?
Yes.
Well, that's better than the other.
Yeah, it's better than the other one. Okay, what's the best way to push or pull?
No, not necessarily. I
Okay, this way or this way. Lefty, loosey, righty, tighty, right?
That's what I.
Make up.
Well, it depends how.
Wait. Why does one loosen and one tighten?
Well, that's the whole thing with that.
Because the way the screw is made, right?
Yeah, that's not gonna.
Some of them are opposite.
On natural gas lines, they are opposite.
And inside paintball guns. A lot of them.
Wow, I wonder why. Because sometimes they're opposite because of the way the object will naturally rotate and it'll naturally take the screw off through vibration.
Well, compressed air in paintball guns.
That's weird. Why would it be backwards?
I don't know.
Probably
They
made
do.
it.
They do make them like that. Very rare. Very, very, very.
Huh.
Rare.
All right.
You know, they all have a standard form clockwise and counterclockwise.
Okay. Shh. All right, we've learned something else. Okay, look, I know it's been a long Thanksgiving break, but you better start paying attention. All right, we've learned something else. That not only where you locate it radius-wise is important, but also the angle at which you apply your force. And obviously how big the force is, right? The bigger the force, the better. So force makes a difference, radius makes a difference, and an angle makes a difference. Okay, so tell me this. If this is my radius out this way, okay? That's my radius out this way, okay? And in most cases, well, in all cases in physics, your force, if that's a vector, and your radius is a vector, right? Then the angle will be the angle in between these two, all right? In an equation like this, all right? So the question is which angle do we want? So let me draw an arbitrary one up here. Okay, if my force is this way, okay?
You're eventually going to put it on.
So this one's going this direction, this one's coming from that direction, right? So the angle theta, where is the angle theta up here? So you need to be able to identify it. Is it 1, 2, 3, or 4?
2.
It's 2, right? Between the 2 points, right? Always between the 2 points. It's like a pair of scissors. Those are the pointy ends of the scissors. This is where it would close, right? So there's theta. So the question is do I want the sine or the cosine? Do I want the sine component or the cosine component? Which one will produce torque?
Sine.
Okay, because the cosine component is down here, right?
Yes.
This is F cosine theta. That one will not produce torque. It's just going to pull the wrench off, right? Okay, the sine component, and I'm going to put the sine component up here. This is F sine theta. It's perpendicular, right? And a perpendicular force will cause you to have torque perpendicular to the radius, right? So we want the sine. So there you go. There's torque. Torque equals Fr sine theta. Now, technically, I want you to write it this way, please. It's RF. There's a reason why I want you to write R first. There's a mathematical reason, which we won't really get into. It has to do with something called cross product in math class. Have you talked about cross products yet in math class?
The point. You said something about point against the x versus using the point.
Yeah. Like
Dot
if
product
you
versus
have A dot B versus A cross B. Okay, you remember that from math class? Okay, this one is AB, cosine theta, sorry. Cosine theta, and this is a scalar. It's called a scalar product of two vectors. Yes? Yes. And this is AB sine theta, and this is a vector. It's called a vector product. Okay, this is called a cross product, and that's called a dot product in math class, because there are two ways to multiply vectors. One gives you a scalar, one gives you a vector. And we've used both of these now. This is like work. Work equals, what's our equation for work? Yeah, it's FD, FX, FR, something like that, cosine theta. And it's work is a scalar, right? But these two are vectors. Okay, and this is a vector product, and that's like torque. Torque is RF sine theta. Okay? Where torque is a vector. Okay? And a weird vector, we'll talk about that, but it's a vector. We'll also run into cross product when we get into magnetism. You've done that last year already. Those of you that took pre-AP physics, actually everybody took pre-AP physics. Remember your right-hand rule thing? Remember those things? No? You did it.
I remember the force going one way or the other.
Okay, well we will cover that in January or February. Okay?
Doesn't it look stupid when we do the same exam?
Yes, you must look stupid or you won't get it right. If you don't look stupid, you're not going to get it right. All right. So there are two ways to multiply. And for a cross product, it's very important that you put them in the correct order. Because if you put them in the opposite order, your vector will be backwards. Will point in the opposite direction. So mathematically, it's important you put radius first. Practically, it's important you put radius first because what happens is students will forget the radius. They'll think of torque and the force that causes the torque, and they'll forget their radius. So always put your radius first. Radius, then force. Okay? All right, so it's only the perpendicular part of the force that causes a torque. All right? So here we can demonstrate that. Here, do that with the door. Okay, grab the door, and pull, right? Why is this put here? Why isn't it put here?
Because you want maximum torque.
Yeah, because it would be very hard to open and close the door right here, right? So like if I tried to close the door by pushing here, it's a lot harder to do than just doing it here, right?
You're just weak.
Arm wrestle for a grade.
Ooh, that would be, that would be awesome.
All right, arm wrestle for a grade, and I'll have him hold my arm here while I'm out. Because he's not learning anything. All right, here's the other thing, is the angle makes a difference. So like if I take this door and I, push.
Don't break it. Don't break it. It's our cabinet.
Or if I pull, okay, you don't get any torque. You can apply a really large force this way, and you won't get any torque.
Yeah,
But you will
break
get it broken.
I will break it probably. But the thing is that, look, in order to get torque, you have to have a force and a radius and the proper angle, right? All three things, okay? All right, so increase radius, increase force, and what's the best angle?
90.
90, all right? Max torque is at 90 degrees, okay? Your force, if it's perpendicular to the radius, you get maximum torque, all right? Maximum torque. All right, questions so far? Doing okay?
We're alive.
What letter of the alphabet is
Ah, good question. What letter of the alphabet is torque? That is the Greek letter tau.
How do you?
T-A-O?
T-A...
Oh,
T-A-O? T-A-U.
T-A-U, yeah.
I think it's
I remember I had to
T-A-U.
learn it.
All right?
It's like,
So,
Is that lowercase or?
capital, it looks like a T, but that's lowercase tau. All right? So it's got a little twist on the top. Oh, looks like that. I'm going to show you a couple of tricks. Trick number one is, this is our equation for torque. So let me give you one that they will probably give you to mess you up. So here's number one. Let's say that we have, here, we'll just make another wrench. All right, so we got a wrench, all right?
That's how I use a wrench right there.
What?
Front.
How you turn a wrench? Okay, now, what if you apply a force this way,
so you're going,
and your radius is this way? Okay? All right? And let's say they give you this angle right here. Okay? Let's say our radius is, I don't know, 1 meter, and our force is 10 newtons, and let's say the angle is 30 degrees. Okay, calculate the torque.
Okay, wait, what?
What's that?
Don't we need to know that one?
Isn't it the other angle?
no, you can't get the one that is.
Okay, and this is perpendicular right here.
Well, guys,
You get it? Calculate the torque, please.
it's like, don't hit the left.
Go vertical.
All right, so caution number one when dealing with torque is the angle.
It's 8.66.
I agree.
Where's the angle theta that we're supposed to use?
Right there.
That one. That's the angle we're supposed to use.
Because it's because the one that's perpendicular is.
All right.
in that sense.
Remember, this is the angle between these two vectors always, okay? So what? How big is that angle?
122.
All right, well, let's go up here. We know these are vertical angles, right? So there's my theta from over here. So that's 30 degrees here, right?
Yes.
30 plus 90, so 120, right? So it should be RF sine of 120 degrees, right? That's what we should have, right? Okay, so caution number one, watch your angle. Just because they give you an angle in the problem doesn't necessarily mean it's the angle you want. Okay, second thing is there's another way to visualize torque, okay? Instead of thinking of torque as RF sine theta, okay, let me erase this one. Instead of thinking of torque as RF sine theta, think about what it really means.
Angle. R force vertical or perpendicular?
Okay, which force do we want? Do we want the force tangent to the radius or perpendicular to the radius?
Perpendicular.
The perpendicular part of the force is what causes the torque, right? So rewrite torque this way. It's RF perpendicular. The perpendicular to the radius force, okay? So like, look over here. Could I have used this 30?
Yes.
Yes.
Just
But what I really want is the perpendicular part of the force, which is this part right here, right? So the perpendicular part of the force, F perpendicular, would have been F times cosine of 30 degrees, right? Okay, so you don't always have to use the angle they give you. You can find the proper angle if you like. But if there's an angle that's convenient to find the perpendicular part of the rate,
how much?
if there is a convenient angle to find the perpendicular portion of the force, then just use it. Stop it. All right? Now, you got that? Okay, so just use the perpendicular force. Now, there's another trick as well. The other trick is this. It's called lever arm. See this force? That's its line of action of the force. Okay? So if my wrench instead was this wrench, if that was my wrench instead, if I applied this force right here, the same force is up here, but applied it at this radius,
There's a change in torque throughout the whole thing.
how does this torque from the brown force and this radius compared to the purple force and the pink radius?
Greater than that.
Equal to this.
They're the same.
It would?
Yeah.
Because it's smaller.
Is it closer in your?
They're the same because look,
Oh, radius is smaller.
here, what does this really mean? This is RF sine theta, but F sine theta is the perpendicular force, right?
Yes.
But what if we rearrange it? What if we rearrange it this way? What if it's R sine theta times F? What's R sine theta? Hey, look. Here's theta here, right? Theta, theta. Vertical angles. So this right here would be R sine theta, right? It's the effective radius. Or
Maximum.
the radius perpendicular to the line of action of the force, also called the lever arm. So this is the perpendicular radius. Ooh, not too many students like that one.
Looks fine. Yeah.
So like for instance, this comes in handy for a problem like this, because this shows up occasionally. If I had a problem like this, and I'm applying a force right here, and I'm trying to tip this box over. So I'm trying to tip it over about that spot right here.
Fancy tip over.
The center mass.
Yeah. So there's a couple of things. Number one is, how much torque am I supplying to this box to try and tip it over? Well, technically, there's my radius, right?
Yes.
There's my pivot point, there's my radius to my point of action where my force is applied, right? But then I got all kinds of crazy angles to deal with, right?
So then just go perpendicular?
Yeah, so what I could do instead is say, look, but my force goes through it like that, right? And there's my perpendicular radius. So that force times that radius would give me my torque.
So that, what? That's like two, what? You can't have two different things.
It's the same torque.
Yeah, but it, oh, okay, that's right.
Mathematically, it's the same.
Mr. Gordon, would that work for tipping an account?
That would work for tipping a cow, that's correct. Actually, here's the center of mass of the system, right? Here's the mg. What's the torque from mg? Well, the torque from mg is this perpendicular radius times this mass, or weight, and here's the torque trying to tip it over, and here's the torque trying to keep it from being tipped over. Does that make sense? Ooh, I'm losing you.
Yeah.
Yeah, but... Thanks, Marcos. I got you. All right. Well, okay, let's back up a little bit. Let's look at torque again. Torque, the symbol tau. Torque equals RF sine theta, where theta is the angle between these two vectors. And torque is a vector as well, which we'll address in just a minute. Okay? You could also write it this way. Torque equals RF perpendicular, where the force, this is the force perpendicular to the radius. Okay? Because only the perpendicular force causes things to rotate. The parallel does not. Or torque equals the minimum radius, or the perpendicular radius, times the full force. Okay? Any one of those. All right? Now, let's talk about units real quick. Units on radius is
Newton meters.
meters, and that's Newtons. So it's meters, newtons, or Newton meters is what they normally call it. Newton meters. Now that looks surprisingly like a joule, but it's not, because this is a vector, and a joule is a scalar unit, and so we just leave it as Newton meters, okay? We don't change anything with it. We just leave it Newton meters. All right? Okay, let's talk about the vector aspect of torque for a minute. Okay? So let's say I have a wheel, and I apply a force this way along the radius, and I'm going to cause this thing to rotate. Okay, which way will it rotate? Around. Which way around? Okay. We end up with these words like clockwise and counterclockwise. And for those of you that grew up in the digital age, clockwise, counterclockwise.
You just lied to yourself.
I didn't. Clockwise, counterclockwise. Yeah, wax on, wax off.
But you lied to yourself.
I didn't.
Yeah, you did.
All right.
You're telling us the truth, but you lied to yourself.
And that's omega, angular velocity, rotational velocity. This is clockwise. All right, now, here's our problem. Torque is a vector. How do we assign a vector to show clockwise? Okay, that's what every student says, is we do this, exactly what Mr. Burren drew. Woo! Unfortunately, that we can't do that.
So torque is different instances.
We can't say gravity's that way and the normal force is that way. Okay?
That'd be awesome.
All right, vectors have to be straight arrows.
So there's multiple.
So how do I designate a straight arrow to reference clockwise? Yeah, well, okay, one of the options is that you put a whole bunch of them on there. Well, that one, and then that one, and then that one, and then that one, right?
There's some in between.
But see, the thing is, you could draw a million of those, right? An infinite number of those. Okay, so here's the dilemma that they had. The dilemma that scientists and mathematicians have is how do you designate a spinning motion or a rotating motion with a straight arrow, a vector, so that it's unique? Okay, because you could draw an infinite number of these things. And so here's the solution they came up with.
Apply a third dimension.
Yes, they apply the third dimension. And what they do is they apply it along the axis.
I was guessing.
Okay? Because if you look at it, you see this axis of rotation? It's a line, right? Ooh, it's a line. And can you draw an arrow along a line? Yeah. But we have still one problem. Do I draw the arrow this way, or do I draw the arrow this way to designate clockwise?
Why in the world would you do that?
We draw it that way, that's
I
correct.
didn't tell you not to do that.
Okay, do you know why we draw it that way?
Is it this?
So it has to do with the fact that most people are right-handed. Give me your right hand. Right
There
hand.
you go.
Thank you.
You have a knife?
Curl your fingers in the direction of the rotation.
Okay, wait. We're looking this way though, right?
This is rotating this way, right? If you curl your fingers in the direction of the rotation, your thumb will be the axle, or the rotational axis, and your thumb points.
Okay, just use. Yeah. Do what you're doing.
Put your thumb on the axis and rotate your fingers around. So which way does the torque vector point? Into the board. Okay, we're going to do this because we're going to end up doing this again when we get to magnetism. So how do we designate a vector? Here's a vector.
It's an arrow.
It's an arrow.
Okay, how do we designate an arrow into the board? Okay, if this arrow went into the board, we would see the tail feathers.
No.
Okay, so this or this means into the board. Okay?
Into the board.
Into the board. what would you see if the arrow was coming at you? You'd see the point, or like that, right?
Flash before your eyes.
Yeah, you would see a poked out eye, right? Okay, so it's either a dot or a dot with a circle around it. So if we were going to do the torque for this one, the torque would look like this. There's my torque. It's into the board.
Oh, so we do X.
So we would do an X, right? Because our thumb, our right-handed thumb points into the board, correct? Okay, so let's see if you get it correct. You're in your car, even if you don't have a car. You're in your car. Hey, let's do it better. You're on your bicycle.
I don't know how to ride a bike.
You don't know how to ride a bike?
Wait,
Really?
my question is, how can you be in your bicycle?
Point taken. You're riding your bicycle. You're riding your bicycle this way. Which way?
The wheels are rotating.
Yeah. Which way is the angular velocity vector pointing for your wheels?
That sounds hard.
Which side of the bike are you on? Are you looking at?
Dude, you're going forward.
Yeah, I know, but which side are you
You're in standard bicycle
No.
position. There.
You're going this way.
You're riding a bike.
The top
So-
of the wheels are going in the direction you
Here's your tire.
You never know.
Which way does the angular velocity vector point?
It depends on which side.
No, it doesn't.
Like that. Like,
Well, it's rotating that way, so
It's
it's
going
going that way.
It's
Axle.
pointing
That way.
that way,
That's very
along the axle, right?
Very strange.
So when you're in a car and your car is going down the road, the vector, the rotational vector, angular velocity vector, always points to the left. When you back up,
It's to the right.
then it points to the right.
That's strange. That is very strange.
Got it?
I understand it, but it's just so weird.
Okay, here, we'll do it again.
No, I get it.
how is it backwards? Like that?
Okay, see which way it's rotating?
It's up.
Hold on.
Get it go, Maggies. Yeah.
Which way's the angular velocity vector?
Up.
Okay, it's rotating this way, so it's going to be up, right?
Assuming we define upward as that way, because people will probably
Wait,
put
it's
up.
down or that way?
Yeah, so if it's rotating this way, it's down.
Yeah, that's not right.
All right. Got it? Got it, got it, got it? All right, so you see that door in the back? The door that's closed. You're going to open the door. You grab the handle. Okay, when you grab the handle, and you turn the handle down. Okay, we'll go back here.
That way.
No, the door itself. It's that way.
I turn the handle down. Got it?
Yeah.
Okay, when I turn this handle downward, which way is the torque vector?
Into the door. Apply the into the door.
Into the door, right that way. Okay, so torque vector on the handle's that way. Okay, when I open the door, which way is the torque vector?
Downward. Well, assuming we're talking about the door.
We're talking about the door.
Downward.
Okay, so the axis is right here, right? And I'm moving it that way. So the torque vector remains down, right? Got it? It's kind of weird at first, right?
Still is.
Dang it. Colin, you should have gone and closed that door.
All right. So there's torque vector. Now, at this stage of the game, for torque, we don't have to worry too much about which way the torque vector is going to point. For us, almost always, clockwise and counterclockwise is going to be great. Okay? So if you want to talk about torque as being clockwise and counterclockwise, that's good. But eventually, in physics and in engineering, you will get to the point where you talk about torques being into or out of the board for clockwise and counterclockwise. Okay? All
And
right.
the AP, what do they require?
On the AP, clockwise, counterclockwise is perfect. I just want to get you into the mode of thinking about that vector because you're going to need that when you get to magnetism. All right? All right. Man, I'm losing my voice.
I just now listened.
Calculate the torque, please.
I haven't drawn the picture.
It's not opposed. All right, what's the torque? No.
It's 60 times 9.8 times 5.
Okay, so this is 5.
Oh, it's 0.5?
Oh, the
0.5.
radius is 0.5?
Okay, what force?
No, that's equal 5. Equal 5.
MG.
Okay,
Yeah. Well, yes, it's MG.
57.17
whatever that turns out to be, right?
Yeah.
So our force is 60 times 9.8. Okay, now the angle, the all-important angle.
All important.
Now, in this case,
What's 180 minus 40?
all right, is that the angle we want?
It could be. Clear.
Okay, here we go.
Both sides is down.
It needs to be perpendicular to the
Okay,
force.
the all-important angle. So the force is this way, the radius is this way, so that's the angle we really should use,
140.
But
which is 140. Wow.
yeah, sine of 140 is equal to 7.
I don't know what angle is
Okay, that is the angle from the equation, right?
Yes.
Because the radius is that way and the force is this way. Okay? Now I'm going to show you a trick in just a second. Okay, sine of 140. So we end up with our answer being, what, 1890?
Yeah.
1890 what?
Oh.
Newton meters. And that's a vector. Hey, which way is my torque vector? Here's my pivot point. Which way does the vector point? Out of the board or into the board?
Out of the ball.
Okay, it's going to
Wait.
try and torque the thing this way, right?
Oh wait, I'm using the wrong hand. That's why.
Okay.
You still think right-handers are smarter than left-handers?
Yeah,
I'll give you that.
right-handers
I'll give you
aren't
that
too smart. All right, this is the reason why we're starting this now, because we wanted to have this out of the way by the time we get to magnetism. Okay? All right, so that's into the board. Or clockwise, right?
Except we don't have a chair.
Now, everybody, shh, listen. What if I had used sine of 40 instead?
It would have been the same answer.
Why?
Sine of 40 and 140 is the same.
Okay, the sine of 40 and 140, the sine of supplementary angles is the same number. You remember that from trig class, and the reason why is because the sine function looks like this. Here's 90 degrees. If you take the sine of this angle and of this angle, you get the same value here, right? Okay? So and these two are supplementary angles. Okay? Or you could just think of it the easy way. This is RF perpendicular. What's my perpendicular force? It happens to be the sine component of this, right? Because I have a force this way, and here's my sine component, right? That's the perpendicular part. Does that make sense? Wait a minute, I think I'm losing you. The sine component is the perpendicular portion of the force in this case, right?
Yes.
Okay, so that's why sine 40 would also work.
Okay.
All right. Now let's do a little bit more practical problem. Something that we really run across in the real world. And let's see.
A hand.
Yes, it's a hand.
A dumbbell, is that supposed to
A dump, that's not nice to call it that.
Oh, okay. Yeah.
That's a baton. That's a baton.
Is that your excuse for muscle?
Yes. All right, here we go. Here's your bicep,
Call an arm.
forearm, hand, barbell, okay? And you are going to hold this barbell in place. The barbell is a 100-Newton barbell.
Why would you buy a barbell and use?
All right. From your elbow connection of where your bicep connects to your arm is about 6 centimeters. Okay, from here to where your bicep connects. Where your bicep connects to your forearm. Okay? From here to here, from the pivot point of your elbow to where your arm is, or where your hand is about 42 centimeters.
You mean where the dumbbell
At least, where the dumbbell's being held. Now, let's assume that this angle right here is 90 degrees. Okay? All right? What force must your bicep produce in order to hold this right here?
Another word for it. Oh, we want a vertical force.
Yes. Now, we'll just call this the force from the bicep, all right? F bicep. Okay, what force must the bicep produce to hold this in place?
Same as G. Oh wait, no.
All right, now, in order to hold this in place, what must be true? What must be true?
Torque equals 0.
The torque must be 0. The force that your bicep applies. Okay, now wait a minute. Let's get this right. If this is the pivot point right here, okay, right here, and you put a weight on the end of this, okay,
You have to apply a really strong force to hold that still.
and you put a weight on the end of this, okay, and if you're pulling up right here, okay, so there's my pivot point, and I pull up here, do I pull up with the same force as the weight of the tape on the end?
No, you pull it with more force.
Okay, same torque, right? So the torque up must equal the torque down, right? For it to be in equilibrium. Okay, so torque up equals torque down. Actually, it's not torque up equals torque down. It's clockwise torques equal counterclockwise torques for it not to rotate. Does that make sense? Yeah. Torque this way must equal torque that way. Okay? So the clockwise torque must equal counterclockwise torque for this to work. So the torques we have are, okay, which is my clockwise? Ooh. Are y'all seeing you need to draw a free body diagram? So here's my free body diagram. There's your arm.
That's a nice arm. Very
Really straight. Why did you do that?
Practice. Okay, where's my pivot point?
Oh my god.
What forces act on it?
Gravitide.
Okay, we got a gravity this way, which is 100 newtons.
Gravitide.
It's important you place it in the right spot. What other forces do we have?
Whatever you're exerting upward.
Okay, the bicep force, upward. Any other forces?
The one bringing it in.
Yeah, there's going to be another force here we're going to find out in a minute. But for right now, these are the two that are causing torque, right?
Yeah.
This one's torquing it
Downward.
this way, clockwise. This one's torquing it counterclockwise, and they must balance out. Okay? Okay, so let's do the clockwise one right over here. Radius first. What's the radius?
36.
0.42 meters. And 100 newtons. That's it, right?
Wait. Hold on.
Okay, this one. What's my radius?
0.06.
And the force is the bicep force. So what's my bicep force?
700.
700 newtons. Okay? So in order to hold up a 100 Newton barbell, you have to pull up with your bicep 700 Newtons. Now wait a minute. Hey, shh, look. Shh. If you're supposedly holding this in place, right? Then your bicep can't be accelerating up or down, right? But we just said this is 700. So what does that look like? If you apply a 700 Newton force here and a 100 Newton force down, what's it going to do?
Stay still.
Whoa, whoa! 700 up, 100 down. How does it stay still?
Torque is equivalent.
There needs to be another force to make this true.
Oh, there has to be a 600 Newton force at the point.
Ah, there's got to be 600 Newtons extra down. Where is that 600 Newtons?
At the point.
Yeah, it's at the pivot point. It's right here. 600 Newtons at your elbow, pushing down.
That's a lot of strain on the one. I got one.
Now, hey everybody. Whoa, whoa, whoa. Well, why doesn't this 600 Newtons affect the torque?
Because the radius is 0.
Okay, everybody, did you catch that? Look,
Radius is 0.
this is really important. The reason why the 600 Newtons doesn't do anything in my torque problem is because its radius is 0. It's at the hinge. It's like if I go up to this door, and if I push on the hinge, it's not going to do anything, right? It's not going to go anywhere. It's like if you take a wrench, put it on a bolt, and then push on the bolt. It's not going to do anything, right? All right. But everybody, this still must be true if you're sitting still. If it's not accelerating. Okay, now look, hey. That means in order to lift something up, your bicep has to produce a force much greater than the object's weight. What if instead you weren't holding it this way? What if you were holding it this way? And your bicep was out like this? Would that still be 700 Newtons from your bicep?
Be more.
It'd have to be more, right? Because that's at the wrong angle to produce a lot of torque, right?
And then the same with the weight thing.
That's why when you do this, you kill me.
Yes, that's why sometimes now if you've ever lifted weights, you know why it's harder to do certain exercises. They're much harder than others.
Yeah, grab a and then put it behind your
Yeah.
Really?
Yeah. Or if you hold it out like this and then lift them, or like down here and lift them, like right at the beginning, it's really hard, right? Once you get them to here, it's no big deal. But at the end, it's really hard because you're at the wrong angle. All right. Yeah, the tricep exercise. That's because your triceps not as strong.
I'm talking about the shake weight.
You get the shake weight.
My mentor at the internship that I had this summer, she actually bought a shake weight and she like worked out in the office. It was hilarious.
All right. Shake weight.
Should buy one.
She did that by
Yeah, it's because it's making you move all your little muscles.
It works it right
Basically, you're going like this.
All right. Shh. Listen up. Hey, you know what? You could lift a lot more weight if you just hook the weight straight to your bicep then, right?
What?
Yeah, you go like
It's like,
put it right
like
here.
how much can you lift like this?
10.
X amount.
Say 50 pounds. No big deal, right? 50 pounds?
20.
Okay? But if you hooked it straight to your bicep could lift it 7 times that amount. No problem.
Yeah, the only problem
Really?
is you'd have to use your other muscles to hold it.
Yeah, the only problem is that your bicep, how far can your muscle move?
Very small.
Okay, look, how far does that muscle actually change length? From here to here. About that far? Okay, so if you want to hook your bicep to your arm a different spot, you can lift more weight.
Because we can do that, yeah.
Yeah, hook your bicep down here.
Just hot glue it.
You have a hollow.
You can lift really heavy weight. But the problem is you could only lift it like that far, right? Okay.
Like they do
Yeah.
in trucks.
Your biceps are hooked in here. Your biceps have to exert much more force than what you actually lift. But what you get in return is this whole big motion of your arm, right? So you can grab things from far away and move them around. All right. Now your jaw, on the other hand, your jaw is attached like this, with your teeth here, because your jaw needs to have a really large force in order to crush food, right?
Yes.
And so your jaw only has to move a little distance, right? I have a board. Come on, everybody, pay attention. I have a board. The board is 100 kilograms. It's very heavy. I have put it on 2 scales. Okay? What's each scale going to read?
50.
50. So it's evenly distributed, right? So what we end up with is this. Draw your center of mass. Here's where your weight effectively is concentrated. And then this one pushes up, force from the left. This one pushes up, force from the right. And because they're evenly distributed, if I'm just going to make this 1,000 newtons. Then this will be 500 newtons. And this will be 500 newtons. Right? Piece of cake. All right, now, what if we do this? Once again, it's 100 kilograms. And I have a scale here. I have a scale here. But now I put a person right here. And this distance from here to here is 4 meters, but this person is 1 meter from this end. And we'll have the person weigh, make it easy, 100 kilograms. Okay? All right, now what does each scale read?
50.
It won't be 50. It won't even be,
And it's this one.
That's what?
it won't even be distributed evenly.
No.
Because which scale is going to read more?
The one, this one.
The one on the left, right?
175.
Yeah.
Okay, so here's how we do this, everybody.
Is that a meter stick?
This is a force problem. It's a 4 meter stick. Okay, everybody, first things first. Will you please draw your free body diagram, and this time it's important that you draw the forces where they're located. Okay? Okay, so draw all your forces on this object, and make sure you draw them where they're located. Okay, we got the one from the center of gravity. What else we got? We got the person one, and that one's going to be right here. And these two are going to be the same in this case.
Oh, it's 100 kilograms.
What else we got?
Then you've got the 2 normal forces.
Okay, we got the force, the normal force on the left, and we got the normal force on the right. Now I've drawn them all kind of the same length. But in reality, this one's going to have to be longer than that one, right?
Yeah.
So let me do that. Just to remind me that that's going to be true. Okay, what do we have at our disposal? We know the object is not accelerating. So what does that tell us about the forces? They all add up to 0. Now, in the x direction they add up to 0, but we don't have any x direction, right? So we don't really care. But the sum of the forces in the y direction must add up to be 0 too. So if we write that equation, what's it going to look like?
NL plus NR equals 2mg.
Or you could do this, minus this equals 0 if you prefer. But NL plus NR equals 2mg. Now we know some of these numbers, right? We know m and we know g. So we could put 200 times 9.8, which is going to be what? 19600, is that right?
Wait.
Yeah. Is that right? Okay.
I concur.
Our problem, though,
Can't prove it against them.
we have one equation and 2 unknowns.
It's
It's 1,000.
Oh, is it 1,000?
Yeah, not 19,000.
1, 2, 10. Oh, yeah, I put an extra one in.
Kinda kill me.
Does that look better? Sorry. There we go. Okay, my math geniuses.
I don't like the sound.
How do I solve that?
Plug in for
It's
NL and plug in for NL.
long, then you divide it by 4, and then it's 1/4 of that thing.
No. You just
I'm going to say no.
well, it depends what's
In math class, what do you do when you have one equation and two unknowns?
system of equations.
You need to find another equation. Okay, look, my x one doesn't help. The y one gives me this. What else do I have?
Well, you need to know the torque equation, don't you?
Torque. Hey, look, the sum of the torques equals,
Yes, I have. The torque.
why does it equal 0? Because it's not doing anything, right? Okay, everybody, this is called a static equilibrium problem. If the object is stationary and not moving, that means the forces this way cancel in the y, the forces this way, x cancel, and all the forces trying to rotate it this way and this way must cancel. Does that make sense?
Yeah.
All right. So the trick is that the really cool thing about this is that where do we pick our rotation point?
The center of mass.
Now you could pick the center of mass, but it's not really rotating, right? And here's the really cool thing. If this is true, you can choose the rotation point wherever you want. Because, is it rotating here?
Ahead of the person.
No. Is it rotating here? No. Is it rotating here? No. Is it rotating here? No. You can pick any point you want. So here's the cool thing, is pick a point that's going to help you out.
At one of the ends, so one of them is 0 radius.
Ah, there are two really good places to pick the pivot point. Either pick here or here. Why does that help?
Because it's 0 radius.
Ah, because it's 0 radius here, then the torque from this one disappears.
So M2 M is equal to N.
Let's pick that one. I like that one.
Let's do his time.
But you could also choose the middle, that way you can get her weight.
Yeah, so
Now you could pick that one, and what you'd do if you did that, you'd end up with an equation with two unknowns, then you'd have a system of equations to solve. It's kind of nice just to do it all in one step. So I'm going to pick the left end, where I put my pivot point, right there. Okay? So, once I've picked this pivot point, how many torques do I have? 1?
Oh wait, no, you
Two.
got down 3.
3.
Yeah.
1, 2, 3. That one? No,
No.
because it's at the pivot point.
Yeah.
And remember, you can pick your pivot point wherever you want, as long as it's not rotating. Okay? Because it's not rotating about any point. All right, now, key thing is what kind of torque do I have from this one? Yeah. Is it this one or this one? Or you could say, is it torquing it clockwise or counterclockwise? Clockwise and? Clockwise and? Okay, so the torque from this one and this one must equal the torque from that one, right? So that means my torques clockwise must equal my torques counterclockwise, right?
Yes.
So I'm going to have an, what's my radius for this one? 1 meter. What's my force? mg. Or my mg is going to be
Well, if we say
980, right? Newtons, is that correct?
Yeah.
And then what's my angle?
It's exactly 90, so it's times 1.
Ah, so sine of 90 is 1, so I don't have to worry about that. I have a sine of theta here, but it ends up being 1, right?
Yes.
Okay, so I've got that one.
I concur.
Well, thank you. Okay, I have another torque here. What's its radius?
2
2.
meters.
What's the force?
980.
980.
Again,
And the
times
same
1.
And then sine of 90, which is 1, right?
3 times 980.
Okay, so is that it? Those are both my clockwise, right?
Yes.
That must equal my counterclockwise. My counterclockwise radius is what? 4.
Meters.
What's my force?
And R.
N R. What's my sine theta?
1.
It's 1. So there you go. So I've got 980 plus 1960 equals 4 NR. So it's going to be, what, 0.492, 2940 equals 4 NR. So NR equals, whatever that is, divided by 4. 735. So the force on the right is 735. Hey, if the force on the right is 735, what's the force on the left?
1960.
Yeah, whatever that is, minus that, right? So I plug that in there and I get the other one.
So did you do
Does that make sense?
Yeah.
Who said you got about 4?
Breathe. Bad. Okay, you got it? All right, let's do another one. You have, by the way, this is 100 newtons. This is 10 meters long. And the attachment right here is 6 meters.
You should just tilt that up a little bit.
Oh yeah, like the one in your homework? We'll do that one next. All right.
I don't think so.
Okay, so you have a beam right here. A beam that's 100 newtons. It's holding up a 200 newton weight. There's a cable right here. And it pivots right here. It's sitting still, not moving. So all the forces must cancel. Okay, I want to know what's the tension in the cable.
Oh no, not that.
Actually, you know what? I want to know what the tension in the cable is, and I also want to know what the forces are over here. So, first things first, let's draw a free body diagram.
You want to know.
Okay, what's the most important part about this thing to draw? The bar. All right. What are all the forces on the bar?
The
Tension.
200 newton.
Okay, we got a tension right here. What else?
The 200 newton.
We've got 200 newtons here. What else? Ooh, the center of gravity one. Where is that? Is that going to be
Well, yeah, the same.
probably the center?
Probably.
It's like if it's not drawn on scale.
You should say you're good. It's not good.
Just questioning your artistic skills.
All right.
I would say.
Now, everybody, is that it?
And now, don't you have?
Why, cheater from Physics C?
Because it's on the. We'll say that's a wall.
Okay, yeah, now look. If with these three forces, can the thing be in equilibrium?
No, because there's a pull.
Ooh, because it's going to want to move that way, right?
Yes.
So how are we going to get a force this way to cancel it out?
Pushing against the
Yeah, there's got to be one right here.
And you blow it up with some bombs.
Now, we're going to call that H for the horizontal force. Now, there might be another force at this hinge, okay? And,
Keeping it up and down.
yeah, keeping this end from moving up and down. Now, I don't know which way that's going to be. Do you have a guess? Okay, raise your hand if you want the vertical force here to be up. 1, 2. Raise your hand if you want it to be down. 1, 2, 3, 4, 5. All right, the rest of you non-voters, we don't know what to do with you.
Just, yeah, whatever they.
We just want it
has
there.
like 3 things you're supposed to.
Okay, that's fine.
That's how it tells you.
All right,
Pretty simple.
everybody. What's the acceleration of my object? 0. Hey, that means that the sum of the forces in the x direction add up to 0. That means the sum of the forces in the y direction add up to 0. And that means the sum of the torques add up to 0. Yay! Okay, let's build this one first. Oh, we need an angle. Where's my angle?
Think of my idea.
I forgot.
Some years.
There you go, 30 degrees. Okay, let's do this one first. X. X.
Okay.
What goes here?
Horizontal equals
Horizontal
equals
equals
tension cosine. Yeah,
tension cosine 30 degrees.
Yeah.
Because there's 30 degrees. Okay, everybody get that? Because this one is in the X direction and there's my X portion of my tension, correct? Okay, let's do Y. What does Y look like?
Vertical.
All the ups must equal the downs, correct? So I got a bunch of downs. V plus 300 equals
T sine 30.
T sine 30. Because there's my ups and my downs, right? All right. Okay, here's my problem so far. How many equations do I have? How many unknowns? Okay, I need a third equation. Okay, now let's be smart. Where should I pick my pivot point?
At one of the ends.
Which end is better?
Because
That's-
that's elevation.
Ooh, why is that better?
Cancel out your vertical.
No torques.
No torque.
No torques. Okay, now, riddle me this. Which ones are clockwise torques?
All the ones going down.
Okay,
No.
okay, clockwise and clockwise.
Yeah.
And this one's going to be counterclockwise, right?
Yeah.
Okay, let's write it out.
They're more the same.
Okay, let's do our clockwise first. Radius first. What's the radius for this one?
Halfway, 5 meters.
5 meters times a force of 100 newtons times an angle of?
1.
Okay, sine of 90, which is 1, right? Okay, plus, I'm going to do, these are all my clockwise, I'm sorry, these are all my clockwise torques. 10 meters times 200 newtons, that's a clockwise, and that equals, because that's it, right?
Yes, 6
Yeah.
meters.
Okay, 6 meters is my radius for that one,
Times tension.
times tension. Ooh, we got an angle this time.
Sine of 30.
Now, remember, I just want the perpendicular part of tension, right? How do I get the perpendicular part of tension?
Take the sine.
It's going to be the sine component, right?
Yeah.
So it's going to be T sine of 30 degrees. Hey, look at this. I got one equation and one unknown, so I can solve for T, and then I can solve for V, and I can solve for H.
All right.
Hey, did you see how this works?
Yeah.
Okay, I want you to try your homework and bring it in because there will be some hard ones on it, and you need to make sure you get it right.
Okay.